Anyone does not understand what do we mean by this? Think? Don't feel shy. If you don't understand it, that's fine. So this statement means that gamma dot is indeed a velocity vector, i.e. it is tangent to M. It lies in the tangent space of M at every point. Very good. So if I have gamma of t, remember gamma of t is written in coordinates like this. Gamma of t, I have some coordinates q1 up to qn or x1 up to xn. Simply, I get the gamma dot by differentiating with respect to time. It's pretty straightforward, very easy to get. Okay, what about the acceleration? Gamma dot is very well defined, but gamma double dot, if you differentiate again, this is not defined as a tangent vector. How come? Well, let's have a very simple example to show. And not even on a curved space, in our R2, gamma maps 0 to some t to R2, two-dimensional space, this ball, okay? The curve is defined by, well, what coordinates you want to use for R2, any coordinates, maybe x and y. If it's x and y, give you, here is cosine t, sine t. So if this is your x and y, here is your curve. Actually a circle, okay? So this is your curve, cosine t, sine t. Well, I can use the xy, but I mean R2, I can use whatever coordinates I like. I may use r and theta. That's perfectly fine. You can transform this guy here from x and y to r theta. R is x squared plus y squared, right? So you get here what? What do you get here? You get 1 as an r. And theta is tan inverse y over x, so you get t. And if you start from here, you can use the inverse relation to get here. X is r cosine theta, y is r sine theta. It's perfectly fine from one coordinate system to another, okay? And the same for the velocity vector indeed. So here is gamma dot. I can differentiate here, that's perfectly fine. If I differentiate this guy, I'll get negative sine t cosine t, which if you plot it, it's just a vector tangent to your curve everywhere. Okay? And I can also differentiate here to get what? 0 and 1. Okay? These indeed are equivalent. What do you mean by equivalent? Is that I start with this guy, I multiply by the Jacobian of the transformation, I get this guy. I start this guy, I multiply by the Jacobian of the other transformation, I get this guy. Multiply by a matrix. Velocities are transferred linearly, right? They are tangent vectors, they are velocities. So this is a velocity vector, I multiply it by a matrix, I get this guy. What's this matrix? It's the Jacobian of the transformation. If you start here, multiply by the matrix, you get this guy. That's fine. So either you differentiate here and transfer, or you differentiate here and transfer, that's fine. Okay? They are indeed equivalent. Okay, let's look at the gamma double dot. Gamma double dot of t is what? This is negative cosine t, put with the red, and this is negative sine t. Versus, now they are not equivalent anymore. Gamma double dot of t is 0 and 0. No single matrix in the world can transfer this vector to the 0 vector over there, and vice versa. You cannot multiply this by any matrix, you'll get a 0 vector, right? So simply double differentiate of your curve will not give you a well-defined vector, tangent vector. Okay? Even in the simple example R2. Okay? So we need some rigorous definition of acceleration. Your acceleration of a curve, gamma of t, is not gamma double dot of t. You need some deep concept of an acceleration. Any questions so far about this example? Any question? Any question, please? Any question? Okay, so let's go here and talk about acceleration. What is acceleration? Can you tell me what's acceleration, please? What's acceleration? Of what? What? Yeah, so it's rate of change of your velocity vector, right? Very good. That's right. Okay, so we need to define how we will differentiate a vector in general. Given a vector, so given a vector, y, for example, okay? And how we can write that y is a vector? It's belong to gamma of m. This is the set of vectors on m, vector fields on m, right? So given a vector, how can I differentiate this vector in general? It can be a velocity vector, can be anything, right? What is the rate of change? What is the derivative of y? And I will be very specific. Actually, when I want to differentiate, I want to differentiate y along a curve. Yes, Patricio?
I have a question about the previous
Sure.
part. So in the polar coordinates, does that mean that this equation for the velocity is linear? Is the line? Because the acceleration is 0?
There's a question? Yeah, that's fine. It's linear. Yeah, the velocity. The velocity is not linear. The velocity is constant.
Right. Yeah. Never
Okay.
mind.
So what I'm trying to say here is that gamma double dot is not everything. Just differentiating twice will not give you a meaningful term, a meaningful identity. Okay, this is not your total acceleration. Maybe part of it, that's fine, but it's not your acceleration. It's not well defined because you cannot transfer it from one coordinate system to another. Okay, the velocity is very well defined. So now I'm trying to get the acceleration, which is the rate time. If the velocity is well defined and it's a vector, okay, let's apply the basic concept of acceleration to this guy. It's indeed the time rate of change of velocity. Okay, so I'll start with a velocity vector, which in general is a vector field, and I want to differentiate it along the curve. So let's generalize a little bit. I'm talking about a general vector now, and I want to differentiate along a curve, or in particular, along another vector. Both x and y are vectors. Along a vector, or with respect to a vector, or in the direction of a vector, okay? All these three has the same meaning. So again, let's look at how we do it in Euclidean space. Here is in Euclidean space, Rn. Here is your vector x. What do you mean by a vector? At any point, gives you a velocity vector, right? Something like this, something like that, something like this, right? At each point, it changes the direction, that's fine, and magnitude. So this is your x. Your y, the vector that you want to differentiate, maybe something like that. Here is y here, and y here is like this, y here is like that, and so on, so, okay? So, if you follow your x, y will change along that curve, okay? That follows x. Y changing, y here was like this, and after a while, y points like that. After a while, it's like this. So in general, y changes as you flow along x, okay? And I want to determine how much y change along x. And we have a very straightforward formula for that in Euclidean space. How do you compute the derivative of y in the direction of x? How do you compute it?
Directional derivative.
Yeah, it's very close to the direction derivative, except direction derivative is the derivative of function in the direction of a vector. Now we're talking about two vectors. So this is the derivative of this guy in the direction of that guy. So the derivative of y as a vector, y has components, y1 to yn. So the derivative of y with respect to all the coordinates is the Jacobian, right? And I simply multiply it in the direction of x. I get this thing, okay? Any question about that? So this is how we do it in Euclidean space. The result is a vector in Euclidean space, and that's fine. Matrix times a vector, you get a vector. But you all know, and should know by now, that this is what?
D.
The D derivative has another part. So this is by itself is not a vector for any general m, right? If m is general, like the example that we had last time on a sphere, you do this just by its own. It's not the result is maybe a vector in higher dimensional space, but it's not tangent to your m. So for my m, it's not a vector, because vectors are only the tangent vector.